One, two, three. Ladies and gentlemen, welcome. I'm John Pugh, Director of Photonic Integrated Circuit and Quantum Technologies at Optica. And this is the third and last of a mini program of Optica online industry tutorials with Quantum Computing Inc., a company headquartered in Hoboken, New Jersey, developing both hardware and software platforms that bridge the gap between classical and quantum computing. Today, in our online industry tutorial, we'll hear about the incredible progress from QCi on Entropy Quantum Computing, or EQC, a novel optimization framework that stabilizes quantum reservoirs into ground states to efficiently solve complex problems. Remember, this is a very interactive event. We have lots of people registered, so please ask your questions in the Q&A Zoom facility, which is in the bar at the bottom of your screen. And we'll address them at the end of the presentation from Dr. Lak Ewan. So Lak is Quantum Technology Lead at tutorial sponsor QCi. Lak, you're already sharing your slides. The floor and the attention of everyone is yours.
Thank you, John. Thank you for the nice introduction. My name is Lak. Nice to meet everyone. I'm the tech lead at Quantum Computing Inc. So today, I'm happy to share our entropy quantum optimization machine, specialized for NP-hard problem and machine learning tasks. The agenda first, I will share detail. What is Dirac 3? How does it work? And then I will proceed to share some of the algorithm developed, specifically tailored for Dirac 3, and some of the application. I will be very happy to share some really exciting benchmarking. And last, we will share thin film lithium nowbate and how it's enable our system to the next scalable evolution. So let's remind ourselves why we want to build a specialized solvers. So it is strongly suspected, not formally proven, that no efficient, that means polynomial time algorithm exists for NP-hard problems. And even that true even for gate-based quantum computers. So algorithm out there like VQE or QAOA are basically hybrid algorithm that also rely on classical to evaluate the energy for feedback. So that's why there's plenty of effort out there that focus on solving NP-hard problem, specialized hardware, including coherent Ising machine, quantum annealer, digital annealer. This system focusing on solving specifically Ising problem, which is a binary optimization problem. So today we're happy to introduce entropy computing, which solve beyond just Ising model. So here we're looking at a optical entropy quantum computing system. The idea is really old and simple. You take your target Hamiltonian and map it into a dissipated operator. So less loss and decoherence create the decay of the evolution of your physical system. So what that means is you take your mathematical problem, the Hamiltonian will map into the eigenstate of the Hamiltonian map into eigenenergy. And given that the system operate as an open system, which introduce loss and decoherence, it has this non-hermiticity that basically guarantee the conversion. What that means is when the system evolution create this imaginary operator, eventually the least loss state from the set of eigenenergy will graduate, will basically survive at the end, and we map that out at the ground state. So the system here including an optical amplifier, a mixer and encoder that could be a system of interferometer. That could basically a Mach-Zehnder mesh that include optical switch, delay line, and beam splitters. And also the loss medium can be a Xeno block gauge or a nonlinear medium, like some frequency, different frequency. And the whole system operate in a feedback system. So the idea, this kind of system is very challenging to build, and the industry aware of that. Like, for example, Mach-Zehnder mesh, best we can achieve right now in hundreds of scale. And similarly, we need a very high Q for the Xeno block gauge to make this happen. That's why, as the first step, we introduce a hybrid implementation, which is what I'm going to focus on discussing today. We combine both optic and electronic to realize the first EQC computing paradigm. So you're looking at the basically what inside directory, the name of our first entropy quantum computing system. The systems including continuous wave laser, variable optical attenuator, electro-optical modulator, nonlinear media. In this case, it's periodic pooling lithium niobate, single photon detector, TAM correlated counter, and FPGA for feedback measurement. So I will break this down into small steps so we understand how does this work. So first, we encoding our problem into time-bin mode. This type of degree of freedom is stable. It is against environmental changes, and we get the advantage of high-dimensional encoding. So the idea is create really weakly coherent state to approximate the Fock state, and that is created by attenuated the CW light sent into our electrical optical modulator. So for example, if we want to evaluate to solve a certain energy, a certain Hamiltonian, here I'm putting out a very simple example, which you can probably solve by hand, which this Hamiltonian with just 4 variables has some interaction term, some linear term. So the way we do is we map the linear loss as the wave function go into our electro-optical modulator. And right now, it's basically in a single photon level, so the wave function has that type of superposition of state. With this encoding, we have each variable is basically represented by each time-bin. So if we break it down, a chunk of fiber and use a reference clock as like a periodic reference clock, where the photon arrival is completely random, and that is how we create our time-bin mode. So the single photon signal basically next pass through the nonlinear media and to convert to a different frequency, but still guarantee the quantum property. In this case, we can use some frequency. The reason we do this is to take advantage of a very low dot count resolution from silicon detector. And by suppress the thermal noise, we basically promote the vacuum noise that intrinsically coming from single photon counting, in this case, Poisson noise. Then after the signal passed through the single photon detector, it will be measured by time correlated photon counter. In this case, when we measure every wave function, it will collapse into a certain bin, And the user, when they run, and of course, we have the choice to accumulate these photon count over multiple loops, or we just take that loop and that equivalent to how much vacuum fluctuation from photon counting do you want in to feed into your system, into your signal. And this we let the user control this feature. And next we that histogram or accumulated photon counting will be fed into FPGA, where it next start to we replace the Mach-Zehnder mesh with the FPGA, that where we basically perform the nonlinear or the interaction term by perform matrix multiplication and create the next feedback signal from the digital to analog converter, feedback into as the RF signal into electro-optical modulator. So this feedback mechanism keep happening over many loops until at some point the probability distribution start to stabilize and no longer changes. And that's when we couple out as our state vector. With this type of system, we have huge advantage in flexible encoding. So, for example, in previous slide, I shared that these variables are basically encoding in amplitude because it comes from photon counting, which is intensity. That represents continuous variable. But if we want to solve a problem in a discrete variable, like integer variable, we dedicate multiple bin to represent one variable, and which bin the photon arrive, that correspond to basically emulate that type of superposition, different position in, let's say for two variable, if it's arrived in the earlier state, that would be 0, in the later, that would be 1. And similarly, we can go to qtrit or qudit. And with the advantage of this type of encoding, we can also mix them together in the same system, where some of the variable we leave them as binary, some of them we leave them as integer, and some of them are continuous. And this type of flexible encoding gives the advantage in like direct mapping from your Hamiltonian into the system without converting into binary. So let's looking at like how does direct perform in a simple problem. So here we have an example that also demonstrated in our paper a very simple problem, but highly correlated, like with high order term. You can see third and fourth order interaction. And it has this non-convex energy landscape. And here multiple local minima, and this is the global minima. So with this, so how we run this on directory, the user basically extract the coefficient of the linear term, second order term, a third order, the tensor of third order, and tensor of fourth order. So break it down all these into matrices, and you feed them into directly at these matrices. So how does the result look like? So in this test case, we benchmark with gradient descent. So here we would like to start in the same spot at gradient descent. And as we know, gradient descent will basically go to the nearest minimum. So in this case, if we start here, it's going to fall down right in this near local minima. So I'm showing the evolution that we actually capture from our system. Every feedback loop, we capture it to plot. The red one is the gradient descent, and the purple one is directory. And we can see that gradient descent as expected trapped in there. But interestingly, directly we're able to bounce around and reach into the global. And I'm showing another position that we start here, directly again, moving to jump out, and similar to other plot. So with this experiment, well, we found it very interesting that the way we measure a single photon count, which spread the probability of arriving at a different individual bin sub and promote that vacuum noise from photon counting somehow boost this system to jump out of local minima, which exhibit the similar behavior like tunneling. And that is a very exciting result for us. And we proceed to develop even more application to solving actual NP-hard problem. So with that, I will move next on different kind of use case and algorithm has been used on Derek 3. So we internally develop many algorithms that tailor natively to our system. We also been collaborate with a company and institution to explore application and also support our customer with their real problem. We work with Rabobank on fraud detection. We also work with a consulting firm to help them with their loss portfolio optimization. We collaborate with the Therapeutic Institute to explore protein folding, and a very long-term relationship with NASA to help them denoise the sunlight. We also develop multiple algorithms ourselves to scale up more than just the size that the system can handle. So for this specific webinar, I would just select a few cases to discuss, but we're happy to share further information in all of them if anyone is interested. So the first case is the maximum click problems. The reason we picked this problem is known to be NP-hard, NP-complete. It's a typical benchmarking for any sort of NP-hard solver, given it's an algorithm or hardware. So maximum click problem is basically you have n number of nodes with e number of edges, and you would like to capture phi the subset where all the nodes that are connected to each other. And this type of problem is very typical in social network, in scheduling, protein folding, machine learning, resource allocation. For example, imagine like in a group of social network and everyone knows somebody and do not know somebody, and the task is you need to find 5 people in that group that they all know each other. That's type of a problem. So interestingly, we able to the Moskine-Strauss theorem allow us to map this problem into a continuous variable problem, optimize a quadratic problem that all the variables are positive and is subjected under some constraint. And this happened to be exactly natively to our system. And the problem is known to have a lot of local minima, which is create trap for deterministic gradient-based algorithm and require a lot of restart to evaluate this. So here we get this DIMAX benchmark that public available. We benchmark with the state of the art of classical heuristic search. The plot I'm showing here is 125 node, which is equivalent to 125 variables. And we able to, which is showing very complex connection here. And we able to find the best known answer. Here we benchmark with the projected gradient descent and also Frank-Wolf method. We try Derek 3 with different relaxation schedule, which basically giving you different kind of mean photon number of different kind of fluctuation. And we found that Derek 3 consistently found really good answer, close to the optimal and also found the best known answer. So this result is quite exciting for us. And the advantage here is continuous variable, and we don't have to map it into binary variable like in a system like quantum annealer or gate-based model. Because let's say if you have multiple level like continuous, and if you want to map to a binary, that means you need multiple variable to represent multiple binary variable to represent one continuous variable, and that will explode the dynamic range and also hurt the solution quality. So we also go ahead and test with even more number of variable up to 500 here with all the known benchmarking. We have pretty detailed result that you guys are welcome to look at. We can publish really soon. But overall, in summary, we see very competitive performance with the state of the art. So in summary, we're able to demonstrate that we have a novel hardware that could be used as alternative way to solve combinatorial optimization with continuous variable. And it actually can solve NPR problem efficiently. And the most important thing is it has this encoding advantage where it reduces computational overhead and reduce the need for approximation in gate-based or in quantum annealers. In Outlook, the next step, we will continue to increase this problem and benchmark with even higher number of variables, thousands of variables, to match with the realistic industry size. And we also going to explore hybrids with different classical algorithm. And the thing we excited the most is we're going to benchmark with to observe the advantage in power consumption. The next problem we'd like to share is a max K-cut problem. This is a very typical standard problem in a benchmarking quantum computing system. But here we bring it beyond just Ising model. We also looking at part model. We're looking at hypergraph. That means it involves high order of correlation. So with the native quasi-continuous encoding, we basically dedicate, let's say for Ising model, we dedicate 2 time bin to represent one variable, one binary variable. And similarly, 3 time bin to represent the part model, and so on. This mass K-cut problem is widely used in many critical applications out there: machine learning, circuit routing, physical modeling, of course, computational chemistry, and also in telecom. So this type of problem solve an example of this type of problem is like, let's say we have a network of telecom stations and they have a lot of interference, and somebody need to go out there and reduce this interference. So they would like to create like a cut, like a separate two group, such that the connection between them gonna have certain weight, which represent the interference. So we're gonna cut in a certain way that we reduce the amount of interference. And that's type of problem. So we benchmarking with semi-definite program. This method guarantee at least 87%, close to the global answer, this algorithm. So here we have more detail in our paper, but I'm showing here that we show very competitive result with higher probability in the best known answer in Ising problem. But when we move to part 3 and part 4, we start to observe answer that SPD we couldn't see on SPD, which we believe that not because our system is better in high dimension, but it just SPD start to struggle at this higher qudit type of problem. And similar to part 4, we observe more interesting result that we cannot see on SPD. And in the hypergraph, where it's also Ising and part model, but with third and fourth and fifth order, we try to benchmark against simulated annealing, and we see pretty similar trend where we start to observe with very low probability, but we start to observe answer that we could not see from simulated annealing. So in summary, we demonstrate solving beyond just max K-cut problems. And this is very important problem for computational physics and also in other industry, bioinformatics, telecom. We show that it can solve NP-hard problem efficiently compared to SPD and gradient descent. And the advantage is we create a way of encoding that provide direct mapping without translate into Ising. The next step, we would like to push the system further to benchmark again, state-of-the-art classical integer solver. We want to reach even more higher number of correlation, and we would like to challenge the directory with realistic, physics model problem. More detail you guys can find in our supplementary of our paper. Another interesting use case that I would like to share is our work with NASA the past more than 2 years already. So NASA has a lot of satellite images that has a lot of sunlight in it, and they will try to get rid of the sunlight noise and recover the re-image for their weather climate change study. And with so much information, it's very expensive. In order to get rid of the noise, they need to increase the signal, which means they need to optimize their hardware, and it's just so expensive to throw the satellite out there with heavy hardware and hard to manage. So we try to support NASA by getting rid of the noise without touching the signal, but just reducing the noise, or we call denoising. And interestingly, the noise from the sun from black body radiation happen to obey Poisson statistic, which is perfect with what we have on directory, also follow Poisson statistic. So we use that to simulate the sunlight noise, and then convert the denoising problem into an optimization problem. So here you can see this is the original image. This is our test case, the original image. We mix with 20 times of noises. So you can see with eyes, but for computer processing, that's a lot. And using our method, we're able to retrieve pretty clear all the main feature. And next we start to increase with 200 noises. So with our eyeball, we can't even see the signal. And still, with our approach, we're able to extract and get rid of that Poisson noise and recover very significant feature. So we're pretty excited about this result with NASA. So the next step, we're gonna continue to improve their LiDAR image, and we need to increase the size of the problem because their image has millions of pixels, which is equivalent with millions of variables. We create an algorithm to batches our break down our optimization problem and parallelize them or series them to resolve this. And there's not much I could share because this still going work with NASA, but summary of our first study is in the paper if anyone is interested. And the last study case that I will share is on machine learning. Specifically in this case, we use fraud detection. So this is quite interesting problem for us. So we're trying to explore to see if directory can support with machine learning tasks, specifically classifying. In this case, we use a public imbalanced cargo credit data set. So as you can see, the red dot are the fraud and the blue are the non-fraud. So it's highly imbalanced, very little amount of fraud. And these series of plot, we plot with different features. So we look at the data set with different perspective to see how the fraud and the non-fraud correlated. And we can see that they completely overlap in different way, demonstrating that this is a difficult problem to classify. Because if the group are separate, then you can like easy to recognize the fraud and non-fraud. So a typical approach is they use neural network, which is we know that it's highly efficient, but we're interested in seeing if we can use a different approach instead of neural network, because it is known that neural network is a black box method, which means you're making decision, you're making the classifying without knowing why. And that means it's unexplainable AI. So we're interested in looking at boosting, which is an explainable AI method that will be able to, helpful for institutions that under a lot of regulation for ethical in AI. So we explore this boosting method where you basically break down this really hard classifier into weak classifier. So for example, in this case, you need to go fraud or non-fraud, which is a hard problem. We can break it down in tiny thing like, hey, are these transactions international? Are these transactions, over the time zone? Like we break it down in weak classifier and then basically map it into an optimization problem. So you're looking for which weight in the weak classifier will give you the best answer. And that is turn it into actually become a non-convex problem, which we know that the timing doesn't scale well when you increase the number of variables. But we have our novel hardware and we're interested to see how this perform. So we create two test bench for this study case. First, we use XGBoost, which is a commercially used extreme gradient boost method. We tested on multiple core CPU and also on NVIDIA L4 GPU using the NVIDIA Rapid AI package. And the method is you take the training data from a cargo data set, you build decision tree, update the weight, let it run on GPU or CPU and continue this feedback system, and then eventually output the way that assemble the classifier you want to use for the real data. So similar approach, we do the exact same thing, but in this case, we use this data set. We might or might not apply balancing, and then generate the weak classifier. Then we take these coefficient of the weak classifier, which is unknown, we need to figure out those weight. That's mapped into a Hamiltonian and feed it directly into directory. And directory will basically give you immediately the weight to construct the strong classifier. So let's see how these two guys perform. So in terms of accuracy, depends on how we balance the data set. As you can see that in terms of accuracy, actually most on CPU perform better than directory when it's very imbalanced. But when we start to apply a best practice on balancing the data, at some point using our algorithm on directory, we actually observe even higher accuracy than XGBoost on CPU. So we're pretty excited about this result that is comparable accuracy. So how does it look like in terms of speed? In terms of speed, as the number of training data size increase, the training time doesn't change at all for the directory method, but it's increased with a certain trend on CPU. And when you change the number of feature, which equivalent to number of variable, we observe pretty similar trend. So with that result, we see if we can increase to industrial size, like realistic size. In this case, we are pushing it, use synthetic data set that developed from that Kaggle data set and train up to more than 60 millions of data size. We use multiple CPU up to 48 and also multiple GPU. And very interestingly, we observe significant speed up using our approach compared to execute on classical hardware. And similarly, we increase the number of features up to almost more than 800 features, which is pretty realistic size. And similar trend, we already see it's exploded on CPU and a little bit better on GPU, but we still provide a better trend. So in summary, we perform this benchmarking with the state of the art. We've shown that we comparable in accuracy and superior in speed. Next step, we're gonna push the speed even higher and start to benchmarking the energy consumption, because in this case, there's a lot of CPU and GPU was used, and we're looking to challenge with beyond just this public data set, but with real data set from industry. This study case is published. You guys feel free to go to our website to replicate and play with your own, fraud detection data. And that's some of the study case I have today. So hopefully at this point, I motivate some of you to try our system. So let me summarize our spec. This is our Direct 3. It solves integer and continuous optimization variable. Right now we can support more than 900 variables, but we can customize to more if needed. We have all-to-all connectivity. We can go from second up to fifth order of correlation, and it consumes very low power, less than 100 watt, which is a few LED light bulb. It's a room temperature, it's rack mount, it's deployable, and you connect to the system via Ethernet gRPC interface. Our system is available on cloud and also on-prem for anyone who is interested to order. If you follow this link, you can get, I believe 10 minutes of free computing time to explore our system. And in the last few minutes, I will just share our vision and why thin film lithium niobate will enable us to the next evolution of the hardware. So my colleague, Dr. Poya Jainat, he already have a webinar on thin film lithium niobate and our foundry. So I'm not going to go there, but specifically, I will just talk how it related to our computing approach. So the goal of us as a company is we want to build scalable computing system. And we are looking at both analog and gate-based, because we believe that analog and gate-based have their own advantage and disadvantages. So why building our analog system is much easier, it's closer to near-term advantage, and also require less engineering. It has less engineering challenges, and it's also laid the groundwork for us to move to the next step on the gate-based model. So the goal is we want to bring our system, even though it is small and compact, but it's still bulky optic. The goal is we want to move that in photonic chip and eventually, increase in computing capacity with really small form factor and power efficient. So these I'm showing are the building block of our computing system. So as you know, we use time frequency measurement. So that means we want to do high dimensional qudit. That means you need to be able to measure accurately in time. and also capture in very narrow frequency. Because the more dimension you have, then the more qubit or qudit you will have. That means you require an ultra narrowband filter. We also need, as we know, the challenge in the industry is create, multi-qubit like with photonic approach. And for us, we using the quantum Zeno blockage. We also would need currently the undeterministic entanglement generation. We need to move it toward deterministic entanglement generation. In this case, we use spontaneous SPDC or four-wave mixing. And lastly, we also need to create our Alexander mesh, or in general, modulate our photon. We need low loss, low VPI, and high speed EOM. So all of these little building block actually can be enabled with really large nonlinear via microring structure. And that is enabled by our thin film lithium nanobate. And I will not bother you guys with the spec and our progress. I think you can find that in Poya's webinar. But I drop here a lot of our paper progress and also on our website if you guys are interested. So because of that nonlinear requirement, we in our computing platform, the Foundry, laser focused on creating the ring resonator with giant nonlinear susceptibility. And so far, what we have achieved is we have maximal the Chi2 coefficient in the D33Z cut. We also achieved the mode overlap more than 90%. We minimal our best with the background noise, also minimal the mode area sub-wavelength. So right now we getting closer to optimize the quasi-phase matching. And the more challenging part is we need to achieve the Q of 10 to the 8, and we a little bit above 10 to the 6 right now, which using not specific tool for lithium nanobate. So that's why our QCi Foundry was tailored to just thin film lithium nanobate. We hope to achieve our goal in the near future. And looking forward, we hope to bring all of our computing system from rack mount into optical chip. And the optical chip will integrate with ASIC, FPGA, with electronic and also silicon for detector and laser to achieve even higher computing capacity, lower power consumption, smaller form factor, and hopefully it can reach to more user than just big institution. It create access to up to individual. And lastly, I'd like to thank you to our very hardworking team. Been working on Direct 3 and everyone in the company give me the opportunity to share our progress today. Thank you, Optica, for having me and for letting me share our progress. And let's stay connected. Thank you.
Thank you so much, Lac. Really incredible progress from QCi again. It's a really technically challenging area. So now it's time to address some questions from the audience. So again, please type your questions in the Q&A facility at the bottom for Lac. We already have some questions. So Harold Kimmy has asked, is there a similar ML-perf fraud data set that could be used?
Is a similar machine learning data set that can be used?
Machine learning perf fraud data center. Yeah.
I think that's up to you. Like feel free to use as long as the problem you want to classify is imbalanced, right? It's challenging. Feel free to use to apply it. Like we have few data set from Rubber Bank. We use this cargo credit. We're trying with other customer. but we can only publish the result of the Kaggle. So yeah.
Sure. And Harold follows up that question with what are your next steps to getting better predictions? Is that to add additional features, additional feature analysis?
Yeah, that's one of the way, more feature because we can handle more number of variable. And specifically the result I share is just on that data set, right? So it might be different when you try a different diverse data set. It could be different that we don't know yet. And also we're very open to hybrid with classical algorithm to achieve even higher accuracy. And another thing is increase the resolution of our analog system because it's analog, so it has limited dynamic range. So when you map the problem, you're like, how can you recognize these very tiny coupling term, right? So if we cannot recognize those terms due to the limited of dynamic range, then that's how you miss it and you lose the accuracy. So that those improving the hardware also will boost with that.
Great. And I would encourage people to go and find out for themselves. But can you say a bit more about the software stack that sits on top of the hardware for this EQC machine? So when people begin to use it, how do they interact with it?
Yeah. So so I'm leading the hardware team, so I'm not the best to answer this. So what I know so far is we have two way of access the system. So if the customer buy the system directly, then we have very low level, we call it EQC Direct software, which you can download from our website. Very low level where you basically give us the matrix. That's all it is. Give us the matrix, we give you the state vector. We make it very simple. Now, we build more complex software stack when you use it on cloud, where you can encode different kind of problem. Our team also build a software stack called EQC models that you don't have to worry about all these matrix, don't have to worry about our formulation. You just need to, take your Ising model, take your part model, or take your fraud detection, take your portfolio optimization, and map it in directly. So EQC model is something you guys should take a look.
Great. And you've talked about benchmarking the energy consumption as a next step. The Dirac 3 unit claimed, I think you showed under 100 watts,
Yep.
and in the rack mount form factor. What are your initial estimations in how its energy efficiency compares to, I guess, GPU clusters when solving equivalent optimization workloads?
Yeah. So we did have, in prelim study, we observe, when the system is idle, when the system run problem, when the system run even larger scale problem. We just want to see how it behave. And it fluctuates just 1 or 2 watts. It's around 25 watts. And then if we add on supporting electronic and fan and other, then it's about 100 watts-ish. Maybe plus minus a few tens of watts. And but when you benchmark power consumption, we have to be very careful. That's why we need more thorough study, right? So for CPU, GPU, you use multiple of them, right? So, but then you take longer to compute. So maybe instantaneously we comparable with CPU, but then you take longer, right? So overall, the power consumption for us, we will consume less. So that's one way of looking at it. It's involved with timing. And the other way is, the instantaneous power consumption. So we see a lot of advantage. We already see advantage. I just don't want to give out the number right now until we have thorough
Sure.
study.
Sure, I think it's clear from what you've shown, the advantage. So you've shown impressive partnerships with banks and even NASA. What kind of ecosystem partnerships are you building? Are you able to share any more information on what you're looking for, particularly? What can the audience give you?
Yeah, I'm not on the business development, so I think I can only answer within my knowledge here.
Sure.
So specifically in like we for me, like someone who builds the hardware, we want to target the hardest problem out there. That's why we're looking to work with like National Lab and a research institute to tackle their complex computational chemistry, protein folding, that sort of thing, and those give us very quick feedback on how we perform, and then we can make the hardware even better. On the other side, our team is also very active, involved with banks, with consulting firm. We have a lot of customers that I'm not allowed to share, but they give us real problem. So that's what we're looking for. We're looking for a realistic problem, like thousands of variable, something you've been using out there. But we have difficulty because no one would like you to see their problem, right? That's considered as a secret data. So they have to like perform their, redaction and give us some simulated fake data. And it's hard for us to tell. So what we're looking for is we know that if you run our system like 10, 15, hundreds of variable, you're not going to see any advantage. We perform the same as classical. So if you out there has some difficult tasks, we would love to take a look. And if you consider about privacy, then renting or having your own system will be the best way.
Great, thanks, Lan. And in the photonic implementation you discussed with the encoding and loss mediums, that those that are kind of useful to you, what's your approach to dealing with noise and decoherence and loss that you don't actually want, the that are induced in your components, for example?
Yeah, so yes, given that our system take advantage of loss, we also facing, the issue with loss as well. And that's why we choose, lithium niobate because it also gives the advantage of low loss. Actually, I might even have a slide about that.
Oh,
So, we have strong light confinement with low loss. And this is actually the most challenging for us to achieve Q10 to the 8 right now. And the um, the other side is if I put a few paper here. So our chief of quantum officer, this is not new to us. He been working on the Xeno blockage for more than 20 years and bring his research from his PhD to his lab and from his lab to the company. So I share a lot of publication and detail on how using quantum Xeno blockage will basically create the decoherent free subspace, and that's where we would like to operate. Uh, that is our main approach. That is the focus for us.
Lack, we start on time and we finish on time. Thank you so much for being with us. I've absolutely loved the 3 industry tutorials with QCi. We've heard from Puya Dianat and Milan Begliabekov on QCi Foundry and Fab 1. I had the pleasure of visiting last week. It's a fast turnaround TFLN prototyping foundry. And then we heard from Prajnesh Vijay Kumar on QCi's unique MU-Core reservoir quantum computing system. And today from you, Lack Yuan, on the tremendous progress from QCi on photonic implementation of entropy quantum computing. My call to all of you watching is to reach out to QCi if you want to explore a pilot or a demo of any of these aspects. You won't be disappointed. So on behalf of Optica, our speaker today, Dr. Lack Yuan, and all at QCi, thank you so much for attending, and thank you for your attention and questions. I'm sure we'll get together again with QCi soon. So thanks all, and bye for now.
Thank you.